Okay, class, to recap what we talked about last lecture, we looked at a closed loop block diagram, and the two inputs to this closed loop block diagram are one, there's a disturbance input, and two, there's a set point change input. And we first derived the open loop transfer function, and via the blue here, it's what relates the measurement that's fed into the comparator. So you imagine opening the loop right here before the comparator. It relates this measurement all the way back, if you follow this blue line, to the error signal. And that's when the disturbance is 0. And then we derive the closed loop transfer functions that tell us how the system responds to both set point and disturbance inputs. And the open loop transfer function appeared in the denominator of both of these closed loop transfer functions right here. We define BIBO stability to be when you put a bounded input into the system and its output is bounded. And BIBO stability is characterized by the characteristic equation 1 plus g open loop of s equals 0. So the open loop transfer function is critical to determining the stability. And you can see that this is the case because the poles of the closed loop transfer functions are the roots of the characteristic equation. Okay? And if the poles of this closed loop transfer function, or roots of the characteristic equation, all have negative real parts, then the system is stable. If any of those poles have a positive real part, you'll see a response mode that grows unboundedly with time, and then it will be unstable. Finally, we last left off where we found that the controller gain, we should always choose it such that the gain of the open loop transfer function, which involves the controller transfer function, is positive, and that will give us corrective controller action. Okay, now let's put all of this to use. Here we have an example. It's a closed loop system under P control, and I didn't specify the gain of the P controller. It's KC. And we want to ask the question, if we have a knob where we can tune the KC, is it possible for it to destabilize this process? So first, let's derive the open loop transfer function. So let me use blue, and I will open up the loop right before the comparator, right? And y is actually fed into the comparator. And this open loop transfer function is going to relate this y all the way back to e, okay? And you can see it has to go through these transfer functions in series, the 3 that cross the blue line. We're assuming the disturbance is 0 for right now, just in deriving the open loop transfer function. And we get the product of all of those transfer functions because the input is fed through those, the input e is fed through those in series. Okay, so it's a second order open loop transfer function. So now what sign should the KC be? The controller gain? Well, we argued up here we should choose the sign of the controller gain to give us a positive gain of the open loop transfer function. So we should choose KC greater than 0 for G open loop of S to have a positive gain. Okay? And we're sort of memorizing that right now, but the real reason is because that will give us the correct controller action, as we've argued here. But it's a nice trick. So, and the reason I call it a trick is because it's tedious to follow through with logic through each transfer function. Think about whether or not it has a positive or negative gain. This is an easy way to find out what sign KC should be. So what is the characteristic equation of this closed loop system? Well, it's 1 plus G open loop of S equals 0. And that applies since G open loop is up here. 1 plus, and let me copy this. 1 plus this stuff. Equals 0, okay? And then we can write this as a polynomial if we multiply by the denominator there. So we have 2s plus 1 times 5s plus 1 plus kc equals 0, all right? And then we can collect like powers of s, and we have 10s squared. We have 7 s's. How many 1s do we have? We have 1 plus kc of them, okay? And at this point, we should note that the roots of the characteristic equation depend on kc. And therefore, since the roots of the characteristic equation determine stability, the stability it can depend on Kc. So you imagine you turn that knob, the roots of the characteristic equation are moving around the complex plane. You could push one of those roots into the right half plane. That would give a root with a positive real part in a growing response mode, and then you'd be unstable. So let's find out if that happens. All right. So what are the roots of this? Well, we can find the roots. The roots are negative b. So this is the quadratic formula. These are roots of the characteristic equation. Negative b. However you memorize the quadratic equation. Negative b plus or minus square root of b squared minus 4ac. So 40 times 1 plus kc all over 2a, which is 20. And this needs to be in a radical. Okay, and I see this is a nice problem because there's an analytical solution. That's why I chose this problem. So you see a 7 and a 49 there. So to get some insights, let's factor out that 49. And then what we'll get is 7 over 20. This is the plus root. Minus root also has that 7 over 20 term. Right. And then we have a 1 here, a minus 1. In the plus term, we take the plus, yeah. So then that 7 was factored out, so you have square root of 1 plus 1 minus 40 over 49, because we factored that out, 1 plus kc. Yep, great. So this is the plus root, and the minus root is this. I'll just copy this. Okay, good. I only want one of those. Good. All right. So now the question is, so I'll write just to clarify what these mean. So 1 plus g open loop s plus minus. So that's a way to denote both of them equals 0. So there's two roots. And the question is, can any of these roots have positive real parts? So possible to choose Kc such that S plus or S minus have positive real parts. So the mathematician would write is a real part S plus 0 greater than 0, or real part S minus greater than 0. If so, it's unstable for that Kc, for that controller gain. Okay, and we can look at this. So this one, this term here, inside the radical, this will always be, this is including the radical, will always be either positive or purely imaginary. Right? Okay, and that holds for both of these. All right, and because of that, S minus, you have a minus 1, and you're subtracting a number that's either positive or purely imaginary. So S1, its real part is always going to be less than 0, no matter what we choose Kc to be. Not S1, S minus. Less than 0 for every Kc. Okay? So it doesn't matter what Kc is, S minus is always going to have a negative real part. So that's good for a stability standpoint. S plus, however, it can be greater than 0 if, because look, you have a minus 1 right here, and then if you add a positive number to it, if this huge number, if this number on the right is bigger than 1, then it will be positive overall. So if we have 1 minus 40 over 49, 1 plus kc, if this is bigger than 1, right? i.e. if 1 plus kc, and then the sign switches, is less than 0, or if kc is less than minus 1. So what this tells us is that the system is not stable if kc is less than minus 1. Okay, so unstable for kc less than minus 1. All right, and it's BIBO stable, so that's good news, for kc greater than minus 1, okay? And actually, we argue that the controller gain has to be positive for the correct response, so it's actually stable for all rationally chosen kc's. So if you choose kc to be the wrong sign, it actually could be okay if it's really small. You could still be stable. However, you choose it the wrong side and it's quite big, then your system will be unstable. Stable for all kc chosen according to the correct sign. So if, assuming the engineer chose kc to have the right sign, there's no possible way for it to make it, for the engineer to make the controller be too aggressive such that it pushes the system to be unstable, okay? So I like this problem because there's a nice analytical solution. You can look at the roots and inspect them to find out what kc makes the roots have a positive real part to drive it to be unstable. So in the next one, there will actually be regions of kc that are the correct sign and make your system unstable. So now the open loop transfer function again, open the comparator right there, follow your signal back to your error, right? And this is the open loop transfer function. It's the product of all of those. So we have kc over, and we have an s plus 1 for the sensor. Now we have sensor dynamics. So it's going to be a third order transfer function, 2s plus 1. So that's your open loop transfer function, relates the measurement to the error. What's the characteristic equations? We have 1 plus the open loop of s equals 0. We need to multiply by the denominator to make it look like a polynomial. So then we have s plus 1, 5s plus 1, 2s plus 1, plus kc equals 0, and it's a third order polynomial. Okay, and then we can find the roots of this numerically. A little tedious to analyze this analytically. I don't even know it's possible. I wouldn't try. Cubic roots are not friendly. So again, I'll copy the same message we had up here. The roots of the characteristic equation depend on kc. So what I want you to imagine is you have a knob where you tune kc, and then it could push those roots in the right half plane, driving your system to be unstable. So what sign should the controller gain be? It should be positive. And that's so that GOpenLoop has a positive gain. Okay, and so now let's just plug in a few controller gains and see what happens. So if you plug in k equals 2, k equals 6, what you'll find is all three roots have negative real parts. There are three roots because that's a cubic. Have negative real parts. And then, because of that, stable. So it's stable for this choice of kc, right? However, if you plug in k equals 15 and then solve this polynomial using your favorite software, I use Julia, what you'll find is for kc equals 15, there are two roots with positive real parts. So two roots have positive real parts. And because of that, even though one of them has negative real parts, it's unstable. Okay, so I can use Julia here. I'm using Julia right now to compute the roots of these. So I can define it. I'll just make a tutorial later of how to use Julia to find the roots, or MATLAB to show you this. So I'll append that later since I'm on my iPad. So now we can look at a simulation of the closed loop response to a set point change. What I did here is I made a set point change of 1. So this is set point. All right, and there's some offset here because it's P control. But I want you to notice that for KC equals 2, okay, the controller takes the output variable, brings it towards the set point. There is offset, but it's stable. If you increase the controller again, KC equals 6, you see it overshoots the set point, you get more oscillations. Still stable. However, if you jack up KC to be 15, then you see quite a large overshoot, and the amplitude of those oscillations grow unboundedly. That's what we see in this simulation. And so in practice, what will happen is the control valve will fluctuate between fully open and fully closed. And that is puts attrition on your control element. And obviously, it's not good for the set point change. So this is a nice simulation. It shows us indeed we can choose KC of the correct sign. So note these are all greater than 0. Okay. So KC greater than 0. Okay. So we'll put a little check mark. These are the correct sign. So the correct sign. And you can choose it to be the correct sign, but if it's too aggressive, then we can have unstable. So controller set at KC equals 15, too aggressive, results in instability. So it sounds weird, bound input, bound output. It just results in instability. All right, so finally, you can see an example where the controller is too aggressive and it drives the system to be unstable, like I've been telling you for the past few lectures, but now we have the mathematics to back it up and a simulation to prove it. And that's because this process has a third order open loop transfer function, whereas some of the simple ones we studied had second order. All right, finally, I want to show you that a P controller can stabilize an inherently unstable process. And this is your inherently unstable process right here. All right, so the question is, note that this process is unstable. Why? Well, its poles, well, it only has one pole. Pole is P equals +1. And this is in the right half plane. And that implies that it's going to have growing response modes. So it has e to the t response modes. And this grows unboundedly. So if you put in an impulse input, you'll see an e to the t term, and this grows. Okay, now this question is getting at what is the gain of this process, because I could have written it as -s + 1, right? And so I want you to get used to thinking about standard gain time constant form for unstable processes. Okay? So this doesn't look like it's in standard gain time constant form, but actually the gain of this is negative. So to see that, let's just isolate the open loop process here. All right, and we have an input u, output y. Let me call this yu. Yu, okay? And now if we put in, so let's say u star of t is a delta function input, all right? Well, then yu is just the transfer function. And what's nice is for a first order transfer function, we can invert that easily. So y star t equals minus 0.2 e to the t. So that implies is you put in a positive input and the output goes to negative infinity. So the output decreases. And so what that means is the gain is negative, okay? And that's because we put in a positive input and the output decreased, all right? So that's one way to see the gain of these unstable processes. But the gain I put in quotation marks is because there really isn't a gain here. If you put in an input, it's going to grow unboundedly, so it doesn't go to a new steady state. But anyways, we need to know the direction that this process operates in order to choose the correct controller gain. And again, we want the gain of G-open loop to be positive. So because the gain of this process is negative, then we need Kc to be negative, okay? So we need Kc to be less than 0 for corrective controller action. Okay, and you can sort of see that if E is positive, right? Because the set point, you bumped up the set point. And if you want Y to be bumped up too, which you do want the controller to do that, once you bump up the set point, you want this to bump up. And therefore, since this decreases if this increases, what you want to do is instead decrease U, okay? If you decrease U, Y will increase, all right? And so we want Kc to be negative. So what is the characteristic equation of this closed loop? Well, it's 1 plus G-open loop of S equals 0. And if we use our G-open loop that we derive, let's see, G-open loop is minus 0.2 Kc over S minus 1, right? And that implies that the characteristic equation is S minus 1 minus 0.2 Kc equals 0. And that implies that S equals 1 plus 0.2 Kc is the root of the characteristic equation, one root. So one root of, I'll say the one root of the characteristic equation. All right, so what we want for this to be stable is this root to have negative real parts. Well, it's a real number, so we don't want it to be negative. So we need the root of the characteristic equation, 1 plus 0.2 Kc, to be less than 0 for stability. Okay, and that means that we need Kc to be less than minus 5 for stability. So to analyze this, well, Kc minus 5, that is the correct controller gain. So what this means is that we need the controller gain to be aggressive enough. So what's interesting is, so here's Kc. Kc, right? So this here is a wrong sign, okay? So this is the wrong sign. All right? But what this is saying, here's minus 5, is that this will be unstable right here. Unstable. So even if you choose the right sign and it's too small, then it's unstable, which is interesting. So here, actually, your controller can be not aggressive enough, which makes sense because you're trying to harness an unstable process. On the other hand, if your controller gain is the correct sign and very aggressive, that's when you stabilize this system. So what's interesting about this is to stabilize this process, we must have an aggressive controller. So first, we should be amazed that we can stabilize it with the P controller. Second, the interesting thing here is that the controller has to be sufficiently aggressive to maintain stability. So I'll say A, sufficiently aggressive.